CERN is one of the world's leading research centres for fundamental physics, and its greatest impact has resulted from major scientific breakthroughs. CERN's Large Hadron Collider and other unique facilities provide the infrastructure needed for scientists all over the world to learn more about the smallest constituents of matter, their interactions, and the origin of the evolution of the universe. While CERN's research is primarily motivated by curiosity, it has a significant impact on society and everyday life. To achieve ambitious scientific goals, advanced instruments and new technologies must be developed, making CERN and the collaborating institutes and laboratories drivers of innovation. CERN, on the other hand, is not without controversy. Whenever they discover something new, they are always in the spotlight, and most people believe they are trying to mess with things they shouldn't be messing with in the first place. So what is going on at CERN these days, and what strange experiments are taking place? Join us in today's video as something strange is happening at CERN that may shock you. The Large Hadron Collider is a particle accelerator that can accelerate protons or ions to speeds that are extremely close to that of light. It consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures that boost the energy of the particles as they travel. The CERN accelerator complex consists of a series of machines with increasing energies. Each machine accelerates a particle beam to a specific energy before injecting it into the next machine in the chain. This next machine brings the beam to an even higher energy, and so on. The LHC is the final link in the chain, where the beams reach their highest energies. Before being forced to collide inside the LHC, two particle beams race towards one another at velocities very close to that of light. The beams travel in opposite directions in separate beam pipes, which are two ultra-high vacuum tubes. A strong magnetic field, maintained by superconducting electromagnets, guides them around the accelerator ring. Some materials enter a superconducting state and offer no resistance to the passage of electrical current below a certain characteristic temperature. To take advantage of this effect, the LHC's electromagnets are chilled to -271.3 degrees Celsius, 1.9 K, a temperature colder than outer space. The accelerator is linked to a massive liquid helium distribution system which cools the magnets as well as other supply services. So what are the LHC's primary objectives? The Standard Model of Particle Physics, a theory developed in the early 1970s that describes fundamental particles and their interactions, has precisely predicted a wide range of phenomena and has successfully explained almost all experimental results in particle physics to date. However, the Standard Model is not complete. Many questions remain unanswered, which the LHC will help to answer. The Standard Model does not explain why some particles are extremely heavy while others have no mass at all. However, theorists Robert Brute, Francois Englert, and Peter Higgs proposed a solution to this problem. When particles interact with an invisible field, now known as the Higgs field, which pervades the universe, the Brute-Englert-Higgs mechanism gives them mass. Particles with strong interactions with the Higgs field are heavy, while those with weak interactions are light. The search for the Higgs boson, the particle associated with the Higgs field, began in the late 1980s. CERN announced the discovery of the Higgs boson in July 2012, confirming the Brute-Englert-Higgs mechanism. Finding it, however, is not the end of the story. Researchers must study the Higgs boson in depth in order to measure its properties and identify its rarer decays. However, just days after the LHC restarted on July 7th, researchers were looking for monopoles produced by the Schwinger effect, a proposed phenomenon in which extremely powerful magnetic fields could spontaneously produce magnetic particles and their antiparticles. The team used the strongest magnetic field ever measured. This magnetic field was created at the LHC by slamming two beams of lead particles together at high speeds. This magnetic field measured 1016 Tesla, which is approximately 2 billion times stronger than a typical fridge magnet, or 100,000 times stronger than the magnetic field of a magnetar, a highly magnetized neutron star. Despite this, the researchers discovered no monopoles, establishing the first firm limits on the mass of these particles. They cannot be less than 70 times the mass of a proton. However, following these experiments, the organization made an unusual announcement. they claimed to have discovered a fracture that had opened up in the Earth's magnetic field, and that this split had remained open for 14 hours. Some speculated that CERN was opening a portal through which something from another world would pass. So, are CERN scientists really opening a gateway to another dimension? Cynthia Sue Larson, author of Reality Shifts and Quantum Leaps, has been on the lookout since CERN restarted the world's most powerful particle collider for the third time on July 5th. Larson was looking for reality shifts and Mandela effects, or evidence of multiple universes, timelines, rips in the space-time continuum, or other evidence that the Large Hadron Collider had distorted reality as we know it. I've been paying attention to see whether reports of Mandela effects might increase now that CERN's Large Hadron Collider fired back up again, said Larson. So far, I've not yet noticed large-scale reports of new Mandela effects in the past day or so, though it does seem there is a large and growing interest in the Mandela effect. The Mandela effect, in which vast groups of individuals uniformly misremember the same pop culture event, is a fascinating conspiracy theory, in part because it is verifiably true. According to researchers at the University of Chicago, it is an internet phenomenon describing shared and consistent false memories for specific icons in popular culture. Their report described an empirically observable phenomena that persisted between individuals and lacked a clear explanation. When people argue that CERN is potentially producing such occurrences, things get complicated. For decades, a combination of conspiracy theorists, experts like Larson, and ordinary people have been looking for an explanation for this communal cognitive dissonance and false memory. Some believe that CERN's Large Hadron Collider, which has helped humanity find and validate an astonishing quantity of new or speculated information about subatomic particles, physics, and the nature of the cosmos, is generating these reality shifts. This theory is especially popular on social media, where a purported whistleblower has repeatedly gone viral, claiming to millions of people that, for example, the particle collider is changing the weather around the world, or that CERN is opening parallel dimensions that cause the change in the climate. Others have shared conspiracy ideas about how the Large Hadron Collider was designed to create wormholes, portals, mirror dimensions, alternate dimensions, and so on. Of course, there is no evidence that CERN has anything to do with the Mandela effect. While Larson and the International Mandela Effect Conference Board of Directors are receptive to the idea that CERN is to blame for some Mandela effects, neither believes it can account for all the Mandela effects they have witnessed. There's another concern, and this is where CERN scientists come in. As a result of their latest experiment, CERN scientists claim that the universe itself is a miracle, as it should not exist at all. Of course, this is a reference to the Big Bang Theory. Though it is the most widely accepted, it is not the only explanation for how everything came to be. The universe began as a point the size of a grain of sand that was impossibly hot, unfathomably dense, and packed tight with matter and energy, according to the Big Bang Theory. Then, of course, it exploded, scattering its contents and eventually generating the cosmos we know today. There are a few flaws with this theory. For starters, there's the Hubble constant, which describes the increasing rate of universal expansion. According to the Big Bang, things should be slowing down or even contracting. Dark energy is the conventional explanation, even though we can't prove it exists. The environment that created the particles that make up the universe as we know it should have produced an equal amount of matter and antimatter. However, the latter is fairly uncommon. Not only that, but a 50-50 split would have resulted in each particle combining with its polar opposite, unleashing an inconceivable explosion of energy and leaving nothing behind except a wide howling nothingness of a cosmos. Nonetheless, here we are. According to one idea, matter and antimatter must be fundamentally different. However, the most recent CERN experiments finds that this is not the case. Each type of atom has its polar opposite, its antiparticle, with the same mass but an opposite electrical charge, according to the Standard Model of Physics, a guidebook for every known particle in the universe and how it behaves. CERN scientists attempted to determine what fundamental difference such particles should have in order to confirm the existence of the universe in this study. They came up empty-handed. Physicists from CERN's base team investigated the magnetic characteristics of protons and antiprotons with amazing accuracy. The findings did, however, support the Standard Model as the particles behaved exactly as predicted. The matter-antimatter imbalance, as it's known, is a hot topic among particle physicists right now, with several teams around the world investigating it. Another possibility is that the LHC may create extremely fleeting and incredibly small black holes. The appearance of these minuscule black holes may indicate the presence of other dimensions. CERN physicists, however, claim that they are not capable of engulfing the planet and would collapse in on themselves in roughly 10 to 27 seconds. That could be true, but how can they be so certain? And all of these weird experiments at CERN makes everyone wonder what these scientists are attempting to achieve. And more importantly, wouldn't it be better if this money and resources were used to benefit the entire world? Let us know what you think of the CERN experiments in the comments section below.